Hi class, Dr. Lindner. Let's take a look at the action potentials. You should review the concept of what we discussed in the previous video. Remember, you should be able to draw out this little graph. You always start with minus 70 down here. Then you put minus 55. Then you can put 0. And then you put positive 30. Not too difficult, 4 numbers to remember. And we know that resting membrane potential is moving this way at minus 70. That's your RMP. And then the minus 55 we call threshold. So we're like this, then some sort of stimulus opens up the inactivation gate to the sodium channel. So you start to get a little voltage change. You get this little bump up like this, nothing too crazy. But as more sodium rushes in and the activation gate opens, boom, you get that increase. This uprise is depolarization. Then the sodium channel shuts and potassium channel opens and potassium rushes out of the neuron. Now you start to get this negative, more negative voltage change where we're moving back in the direction of resting membrane potential. This is repolarizing. And then the potassium channels are still open. Look what happens. It dips a little bit below minus 70, but then the sodium potassium pump kicks in and we start to come back up here, back to minus 70, which is resting membrane potential. So this is RMP. This is a little threshold. This is depolarization. When you hit positive 30, that's where the sodium gates close and the potassium opens. And then you start to move in a more negative direction. That's repolarization until you get to RMP, but the potassium channels are still open. They're slower to close. So we get to that hyperpolarization right here, where it dips maybe even to minus 90 before we come back to RMP. So the action potential spreads, or they use the word propagates, over the surface of the axon membrane. As sodium flows into the cell during depolarization, the voltage of the adjacent areas are affected and their voltage gated sodium channels open. It's like dominoes. You tap one domino and they hit all the others. So they refer to that as a self-propagating message along the membrane. So the traveling action potential, the AP, the traveling action potential, is called a nerve impulse. Now, there are certain ways, certain things that could be done to block nerve impulses. And in order to block them, we want to try and influence the sodium channels. And what we can do is we can do things that prevent the opening of the voltage-gated sodium channels. There are certain things that can be done to try and ensure that the nerve impulses don't get transmitted by blocking the sodium channels. And what does that are certain anesthetics. These local anesthetics are trying to prevent, that's the cell membrane, and then you have your sodium channel, right? It's trying to prevent sodium from rushing in. All right, so you can have local anesthetics. This is what happens when you go to the dentist and they give you Novocaine. It blocks the sodium channels. Lidocaine does the same thing. You can also use ice. When you hurt your ankle or sprain an ankle and it hurts, you can minimize it by putting ice on it. Ice doesn't block the sodium channel, it just slows them down quite a bit. Ice slows it down. Now, in terms of conduction, there's continuous conduction versus saltatory conduction. Saltatory conduction is what takes place in areas where we have myelin. Continuous conduction takes place where there's unmyelinated fibers. Where we have myelin, if you think back, where if this is an axon, and then we have a Schwann cell here, and then we have a Schwann cell here, and then we have another Schwann cell here. The gaps in between the Schwann cells are unmyelinated, and those gaps are called the nodes of Ranvier. So in saltatory conduction, what ends up happening is the action potential spreads very quickly, and then it leaps, and then it travels through the myelinated section, and then it leaps again, right? Because there's no myelin here. So saltatory deduction, that is conduction, the term saltare means to leap or to jump. In axons that are unmyelinated, there's a step-by-step depolarization at different portions of the axolemma. So if we were to compare, the left side versus what we have here on the right side, on the left side is continuous conduction, and on the right side, we have saltatory conduction. If we look at this neuron on the left, we see the dendrites, we see the cell body, the nucleus, and an axon, and the axon terminal. All of these on the left are unmyelinated. If we look on the right-hand side, these axons, it looks like these are Schwann cells. And you see we got the node of Ranvier, which are the unmyelinated gaps, those sections. So if we look at the time, this is 1 millisecond, 5 milliseconds, and 10 milliseconds. If we look at 1 millisecond, we got sodium rushing in, you got more sodium rushing in at 5. Since this is unmyelinated, we have depolarization and sodium rushing in at different aspects of the cell membrane along the axon. So at 10 milliseconds, the distance is right here, right? The action potential hasn't even gone past the midpoint of the neuron. But at 1 millisecond and 5 milliseconds, there isn't much of a difference when we compare continuous conduction to saltatory conduction. But look what happens at the 10 millisecond. Boom, this is already leaped over almost to the end of the axon terminal. So this one, the saltatory conduction, is the nerve impulse conduction in which the impulses jump from node to node. Saltatory conduction is much, much faster than continuous conduction. And we know that because we know that myelinated neurons tend to fire faster. Myelin speeds up the conduction of the impulses, which is why when it's unmyelinated, let's say you have a condition like MS, multiple sclerosis, which is an autoimmune condition, an attack against the myelin, the nerve conduction starts to distort and slow down. The only place a local depolarization may happen, if at any place it makes sense, it's going to be in the unmyelinated sections like it does here. But other than that, they leap. The conduction leaps from node to node. What are some factors that affect the speed? Well, we know that myelin is one of the things because we've seen it here. If it's myelinated, you have saltatory conduction, it's much, much faster. The size or the diameter of the neuron makes a difference, and temperature. makes a difference. If we look at the size or the diameter of the fibers, we'll see that A fibers, these are the largest, okay? These are also myelinated. The C fibers, these are the smallest, these are unmyelinated. So which is going to be the faster ones? Well, the larger, more myelinated fibers are going to conduct the impulses much, much faster. We know that the myelinate is going to use that saltatory conduction. So the A fibers, these are the largest. It's going to go these are about 5 to 2 microns in diameter, and it can travel 130 meters per second. That's super quick, super, super fast. This is going to be what happens at the neuromuscular junction, right? Those are myelinated, somatosensory, and motor to skeletal muscles. Your C fibers, these are the smallest. These are unmyelinated sensory and your autonomic motor neurons. These are going to be the slowest because they are the smallest and they're unmyelinated. These are the type of neurons that give you the sensation like a dull ache or a pain that you're having, like an aching or a diffuse type of pain that you have, or a burning type of sensation, or you can feel a burning type of pain. Those use these C fibers. Okay. The B fibers, these are medium. These are myelinated. They're myelinated visceral sensory, like being able to tell that your bladder is full or your stomach is full, right? Those are visceral sensory neurons. Okay, so the A fibers are the fastest and the C fibers are the slowest. The resting membrane potential of a neuron, is minus 70 millivolts, but the resting membrane potential of skeletal muscle and cardiac muscle, those are about closer to minus 90 millivolts. So the fastest nerve conduction velocity is 18 times faster than the velocity over skeletal muscle fibers. Nerve fibers are much, much faster to fire. Why? Because they're closer to threshold, right? If you're more negative, you're further away from threshold. Minus 70 is closer to threshold. Okay, when we come back, we're going to talk about synapses and some neurotransmitters.